Welcome to the last class of the semester. We're going to be finishing up chemical thermodynamics, and then you're going to review for your final exam, take your final exam, and then enjoy your summer. So this is chemical thermodynamics part 4, and let's get started. Chemical thermodynamics part 4. All right, so we've discussed equilibrium, Gibbs free energy, and enthalpy before. And now we're going to continue looking at how equilibrium and Gibbs free energy can be related. And hopefully you've seen this equation before in Chem 1 or Chem 2. We're just going to be reviewing it. So you're changing Gibbs free energy at standard temperature and pressure, which recall is denoted by this little superscript, is going to be equal to the negative of our gas constant times our temperature in Kelvin times the natural log of our equilibrium quotient. So we know that the change in Gibbs free energy is going to be the summation of the change in Gibbs free energy of the products minus the reactants, but we can also set it equal to negative RT ln KEQ. So this is the gas constant, which is 8.314, or I'm sorry, 3.181 joules mole Kelvin. And temperature is going to be in Kelvin, temp in Kelvin. And then this is the natural log of the equilibrium quotient. And remember from chemical thermodynamics part 1, the equilibrium quotient was the products to their powers over the reactants to their powers. All right, so changing Gibbs free energy at standard temperature and pressure is negative RT ln KEQ. And KEQ is equal to E to the negative change in Gibbs free energy at STP divided by RT. And this is just rearranging this equation. But so now we know that we can solve for KEQ with known concentration of the products and the reactants, or we can solve KEQ with information about Gibbs free energy and the temperature. Some general rule of thumb about this equation here. If we have KEQ, I'm making a little table. If we have the natural log of KEQ, that should be ln. And then we have the change in Gibbs free energy here. If our KEQ value is greater than 1, so we have our products that are greater than our reactants in general, our KEQ is greater than 1, our natural log of the KEQ of a positive value is going to be positive. And our change in Gibbs free energy is going to be negative. So this is for a reaction that has more product favored. If we have KEQ that's equal to 1, this means we are at equilibrium. And our natural log of KEQ is going to be 0. And our change in Gibbs free energy is going to be 0, which at equilibrium, change in Gibbs free energy is 0. KEQ is equal to 1. This means our products are equal to our reactants. And then if we have our KEQ that is less than 0, this means our natural log of KEQ is going to be negative. And our Gibbs free energy is going to be positive, which means it's reactant favored or non-spontaneous, and it's not going to be proceeding forward spontaneously. All right. So This equation is helpful if we are at STP, but what if we're not at STP? What if we're not at 25 degrees and 1 atm? We can still use this equation, but we're going to need to incorporate it with the overall Gibbs free energy at any given temperature or pressure, which would look something like our change in Gibbs free energy is going to be equal to our change in Gibbs free energy at STP plus RT ln of Q. So here we are at STP, and here not at STP. Here we have Gibbs free energy at STP plus RT ln of Q. So this is the same as this equation rearranged, but here we have this Q value. And this Q value is not equilibrium. So this is our reaction quotient not at equilibrium. Q equals reaction quotient. And this is not at equilibrium. If it was at equilibrium, Q would equal KEQ. All right, but our Q is going to look very similar in form to KEQ because it's still a reaction quotient. So it's still going to be our products raised to their power divided by our reactants raised to their power. And this is just generic for whatever products and reactants you have. If you have 3 reactants in one product, it would be A, B, and C, D, something like that. But Q and KEQ, while very similar in composition, KEQ is when all of your products and reactions are at equilibrium. So the rate of your forward reaction is equal to the rate of your reverse reaction. Where Q can be at any point in time, any temperature, any pressure, not at equilibrium. So it's really helpful to relate KEQ and Q together. We can use them to tell us things about the chemical reaction. So if a chemical reaction is run and we get some concentrations at a known temperature and pressure, we can figure out Q. And then there's tabulated data from years and years of scientists running experiments about various KEQ values. So if we compare Q and KEQ, we can tell if the reaction is going to proceed forward or in reverse or anything like that. All right, so say we have something like Q, our reaction quotient, is going to go from 0 all the way until some very high value. We're going to just mark it as infinity. And when when Q is low, it's similar to KEQ. When Q is close to 0, that means that we are at all reactants. And this is just ratio math, right? So if we're close to 0, that means our top value is really small or our bottom value is really big, enough to make the top value negligible. That would put us close to 0. So we are all reactants. Vice versa, if our value is very, very big, that means that our products are very, very big, and we are going to be all products. This is the same general rule of thumb that we applied to KEQ. But Q can change over time. So as you run across different temperatures and different pressures, Q can go from 0 all the way up to however high of a number you can get, thousands higher. So the thing about KEQ is that it is at 1 point. So this might be our KEQ here. And this is at equilibrium. It's only an instantaneous point. So at some given temperature and pressure, our KEQ is going to fall on a line. And then we can tell if our Q value is higher than this KEQ value, we're going to be going in the reverse reaction. But if our KEQ is higher than our Q value, we're going to be going in the forward reaction. And this should make sense, right? If we have a Q value at 0, but our KEQ is at 6, well, we're going to be proceeding forward and getting more and more product until we reach 6. If our KEQ value is at 6, but our Q value is at 600, we have way too much product, and it's going to be going in the reverse reaction until we get to a 6. So we can tell from our Q value which way we're going. So if KEQ is greater than Q, so if KEQ is greater than Q, we have more reactant and we are going to be going forward. forward because we have more reactant than we do at KEQ. If KEQ is less than Q, this means we have more product. So if KEQ is less than Q, that means we have more product, and we are going to be going in the reverse. All right. So we have our Gibbs free energy equations, which we can use to isolate either KEQ or Q, depending on what we're looking for in a situation. Remember, thermodynamics, all about equation manipulation. Here are some important equations for chemical thermodynamics. All right, so I'm gonna run a couple of example problems, and then we are done with chemical thermodynamics and done with thermodynamics. I can hear you sobbing out of sadness in the background. It's been so fun. All right, so here's an example problem. We have, what is the change in Gibbs free energy for melting an ice cube in a freezer at -10 degrees Celsius? What is the change in Gibbs free energy for melting an ice cube in a freezer at -10 degrees Celsius? So for a point of reference, your freezer in your house is probably between 0 and -4 degrees Celsius. For this problem, we are given our change in enthalpy for fusion, 6.01 kilojoules per mole reaction. And our change in entropy is going to be 22.0 joules per mole reaction Kelvin. And these are for H2O, and these are with fusion. So fusion meaning creating ice from water, liquid water. All right, so we want to know our Gibbs free energy for melting an ice cube at -10 degrees C, which means we are not at standard temperature and pressure, which makes sense because we don't have the little superscript. So what other equations do we have for Gibbs free energy? Well, we know that Gibbs free energy is equal to the change in enthalpy minus temperature times the change in entropy. We also know it's the sum of the products minus the sum of the reactants. And we know that it's also equal to Gibbs free energy at standard temperature and pressure plus the reaction quotient. So out of these equations, which one seems the most relevant for this problem? Gibbs free energy is equal to enthalpy minus temperature and the change in entropy, right? So this is the equation that we want to use. But recall, our temperature here needs to be in Kelvin, so it needs to always be a positive value. So if we have our temperature is equal to -10 degrees Celsius, we add 273 Kelvin, and we get 263 Kelvin as our temperature. So then if we go delta G equals delta H minus T delta S, our delta H is 6.01 kilojoules moles reaction minus 263 Kelvin. Entropy would be 22.0 joules per mole reaction Kelvin. I can tell right now I have kilojoules here and joules here, so I'm going to need to be changing one of those. So I'm going to change the 22 joules per mole reaction Kelvin to kilojoules. So 6.01 kilojoules moles reaction minus 263, and then 2 kilojoules mole reaction Kelvin. Then this would give me 6.01 kilojoules moles reaction minus 5.79 kilojoules per mole reaction. Check my math, just in case. And this gives positive 0.22 kilojoules mole reaction. So this positive means not spontaneous. So when we think about this, we put an ice cube in a freezer at negative 10 degrees Celsius, and we want to look for the potential for it to melt and release energy. And we find that this is positive, meaning that it's not going to melt at negative 10 degrees Celsius. Does that make sense? Yes. If you put an ice cube in your freezer, we don't expect it to melt. In fact, we expect probably the reverse reaction of freezing to be spontaneous. So that logic check, that all makes sense. Checks out. All right. So here's our answer for this example problem. All right, so let's keep going. Here's another quick example. We have this reaction, 2 nitrous oxide plus oxygen goes to 2 nitrate. All right, so 2NO plus O2 goes to 2NO2, and these are all in the gaseous form. And we know that the change in enthalpy for this reaction is negative 120 kilojoules mole reaction, which means it is exothermic. We also know that the entropy change for this reaction is negative 50 joules per mole reaction Kelvin. So we know that it's becoming more ordered. It's becoming less chaotic. So these are kind of conflicting, right? We have exothermic, and we also have a negative entropy, which means that it's becoming more ordered. So when we look here, this will be negative, but this becomes positive. So we need to determine when we will still have a negative delta G here. So at what temperature will this reaction be spontaneous? At what temp will this reaction be spontaneous? We know delta G equals to delta H minus T delta S. We know negative 120 is our enthalpy, kilojoules mole reaction, minus T, delta S is negative 150, joule mole reaction Kelvin. So convert this to kilojoules would be 0.15 kilojoules mole per reaction Kelvin. Set delta G equal to 0 because everything above 0 would then be, below 0 would then be a spontaneous reaction. So that's the threshold of when it turns spontaneous. So we have 0 equals negative 120 kilojoules mole reaction minus temperature times 0.15 kilojoules mole reaction Kelvin. Solving for temperature here, we get 800 degrees Kelvin. So this is, think for a second, I'll give you a couple minutes. This is the temperature that this reaction is spontaneous. Is it also spontaneous above this temperature or below this temperature? Like, is this the highest possible temperature or the lowest possible temperature for spontaneity? Hopefully you thought that this is the highest. So any temperature below this, it should be spontaneous, right? Our delta S times T should be lower than our negative enthalpy at any temperature below this. At temperatures above this, we are no longer spontaneous. All right. I have 2 more example problems, and then we're done. All right. So for here, let's go, example. We have some reaction here. A plus B goes to and from C plus D. We know our reaction quotient is C to C, D to D, A to A, and B to B. So if we are asked, what is the reaction quotient of the following? What is the reaction quotient of? We have CO, gas, carbon monoxide, plus water, vapor, goes to 2 carbon dioxide, and 2 H2O gas. All right, so the first thing that we do when we look at an equation is we see if it's balanced. Is this equation balanced? It's not. So we have 2 carbon dioxides and we only have 1 here. So we need to make this two. And then we have 2 oxygens. We now have 2 oxygens, but we have this 3rd oxygen here. So we need to multiply water by 2. And then we have 4 hydrogens, 2 oxygen, 2 oxygen, 4 oxygen. So now, okay, carbon. We have 2 on this side. Oxygen, we have 4. Hydrogen, we have 4. On this side, carbon, we have 2. Oxygen, we have 4. Hydrogen, we have 4. All right, so now we're balanced. But when we look at this equation, we see 2, 2, 2, 2. So would it be appropriate to say that our equation could also be written as this? One, 1, 1, 1. Yes, that is we're saying the exact same thing. So when you're first given an equation, you need to make sure, number 1, that it's balanced. So check balanced. And then check if it can be reduced. So balance it and then check if you can reduce it. And then you can look at the quotient, which would be CO2 to the 1, H2O to the 1, CO to the 1, H2O to the 1. All right, so this is our generic reaction quotient, which would be CO2, H2O, H2 over CO, H2O. So this is our reaction quotient for this product, for this problem. Okay, so what if you're given that we have 1 mole of CO, 1 mole of H2O, 2 moles of CO2, and 2 moles of H2. Then our reaction quotient would become CO2, we have 2 moles, 2 moles. H2, we have 2 moles. CO, we have 1 mole. And H2O, we have 1 mole. So our Q becomes 4 for these concentrations. So if KEQ is 0.5, then which direction is the reaction proceeding? Then which direction is the reaction proceeding? All right, so KEQ equals 0.5, Q equals 4. So KEQ is less than Q. And if we think about this, KEQ is smaller than Q. If we think about our line of Q going from 0 to infinity, we have KEQ somewhere in the middle. If our KEQ is smaller than our Q, that means that our Q has more products and it's proceeding in the reverse direction. So our answer is reverse. All right. I have one more example problem and it's easy. All right. Example, given nitrogen gas plus oxygen gas, 3 oxygen gas. Or actually, I'm gonna make this aqueous, oxygen aqueous. Just make that G into an AQ. Nitrogen and oxygen are gonna form ammonia. 2NH3 gas. We have N2 at 0.04 mole, H2 at 0.09 molar, ammonia at 0.5 molar. And we want to find, if KEQ is equal to 500, which direction is the reaction proceeding? If KEQ is equal to 500, which direction is the reaction proceeding? So in order to compare to KEQ, we need to find Q. Q is going to be equal to our products raised to their stoichiometric coefficient divided by our reactants. And we know their concentration, so 0.5 molar squared over 0.04 molar and 0.09 molar cubed. So right off the bat, 0.5 is much larger than 0.09 and 0.04, and it's squared. So I can tell just by looking at this that Q is going to have a large value because my products are a large value and they're squared. So when I run the math on this, I do get Q is equal to 8.6 times 10 to the 3, roughly. And I know that my KEQ is equal to 500. So KEQ is less than Q again. And if I look at my Q from 0 to infinity, this is all products. This is all reactants. My KEQ is somewhere in the middle here at 500. And if my Q is over here at 8.6 times 10 to the 3, then I know that I'm going to be proceeding in the reverse reaction. If my KEQ had been equal to 8.6 times 10 to the 3, then what would the situation be? The equation would be at equilibrium. And if KEQ was equal to any value above this number, then it would be proceeding in the forward direction. It would be producing more and more product. So we can also use Q and KEQ to determine molar concentration of reactants or products by manipulating some of the equations that we looked at before, right? So if you know the concentration of carbon monoxide, carbon dioxide, and H2, and you want to figure out the concentration of water, Q, you can use that as the one thing that you're isolating and solving for. It doesn't always have to be solving for Q. It can be solving for a concentration in here, just more equation manipulation. Okay, so that's what I have for chemical thermodynamics. I've also uploaded a helpful PowerPoint under the module for chemical thermodynamics. There's a lot of helpful Khan Academy videos, a lot of helpful online resources if you feel that this went a little fast. I'm expecting that you guys have seen a lot of this before in Chem 1 and Chem 2, and I just wanted to help you remember some of these concepts and go through them. So hopefully you all feel comfortable with this. It will be on part of the final, but recall the final is cumulative. So I'll send out more information about that soon. But I hope everybody has a good rest of their day. Thanks. Bye.